kind of a silty dolomite. Dolomite often recrystallizes, and so even if it's a dolomitic mudstone, it may be coarser grained than what muds are. So that probably is burrows right there, and you can see them in cross-section on the side of the rock as well. Okay, what's next on here? Let's do this one right here. This is a sandstone right here that has pebbles in it. Now you can call it a pebbly sandstone, or you can call it a sandy pebble conglomerate, if you will. There are lithic clasts in here, so some of these are actually chert clasts, so some of the dark clasts in here are chert. They're well rounded though, and the quartz is in here as well. This comes from the Pennsylvanian in Arkansas in the Ouachita Mountains. It's actually from the Gray Spillway. And the interesting thing about this rock, if you look at it, it's probably up that direction, but I'm not quite sure, is all the pebbles are actually floating in it, as though these things were actually deposited en masse. So this was come down as essentially a sediment gravity flow. And this has a sort of fabric that people have described as frictional. A process that occurs like this is called frictional freezing. So frictional freezing, so the whole mass would come to rest, and the pebbles would be locked in place essentially that way. It's surrounded by matrix that's sandstone. This is a bimodal pebbly sandstone, if you will, too. So the modes are, in fact, you'd have the pebbles themselves, or the sand grains that form the matrix would be the other mode, if you will. That's what bimodal refers to. But this one's pretty dramatic that way. This is the very top of the succession at the Gray Spillway. These things, this is a Pisoid grainstone. There's a little bit of open porosity in it, but you can see the laminae that build up around each one of these grains. Each one of these grains has, these layers are relatively uniform in thickness, and so that indicates that it's probably some physical process and not that it's microbial in some way. There's also, it seems to be some sort of competitive growth, so they're smaller at the bottom and get larger at the top. And so these pisoids, anything that's larger than 2 millimeters can be called a pisoid as long as it's a physical process and not a biological process. If it was biological, we would call it an oncoid. But it's too big for an ooid, in other words. So ooids would be 2 millimeters or less. So these things are all fitted together and they're resting on one another, so you can obviously see that it's grain supported. Sometimes these things also have what they call pendant fabrics. Pendant meaning that there's something hanging down from them, like a necklace would have a pendant on it. Well, the pendant is the part that hangs down. So sometimes drips form at the bottom of these things, essentially, where the carbonates will actually be deposited preferentially at the bottoms of the grains. Tells you the up direction, which is kind of close. The pendant fabrics are another up direction indicator. That's a Pisoid grainstone, probably from the Permian in the Carlsbad Cavern area. I won't say who grabbed it or when they grabbed it, and I'm not sure when that was, but this probably comes from the Carlsbad Caverns area. These types of Pisoid grainstones commonly fill in around teepee structures, these sort of lily pad sort of ponds, if you will. They can accumulate thick accumulations of Pisoids like this. What else to tell you? Let's do this one right here. It's from the Monterey Formation. This is actually a diatomite, or diatomite, as some people would say. Very light, highly porous. Quartz has a density of 2.71, I think it is, or 2.67. And so this has a lot of porosity in it, so slightly lighter than the typical quartz. Diatoms are made out of silicious material, and they're usually made out of, I think it's opal, and opal B or something like that, beta opal. And in diagenetics, once this stuff gets buried, it'll actually convert to another variety of quartz, if you will, to and drives the water off, and so there's a lot of porosity that comes available from this because of that. So this is a major petroleum reservoir rock in Southern California. In the Timbler Range is where this was from, and also where this was from. This is more of the same rock, except this is more dense, and you can actually see laminae in it. So this is a diatomite, and this is more of a silicious mudstone right here, I would call it. Silicious mudstone, you can tell that it was actually deposited by traction currents. That's what the laminae would tell you in this case. So you can see the up direction there, and these were all deep water deposits pretty much. So these things in coastal California would have accumulated in relatively cold water, and even in the Central Valley, these things would have been in depot centers that were relatively deep water as well. Up to 30,000 feet of this rock, I think, was deposited in this basin, the sub-basin in the Central Valley. So anyway, that's the Monterey Formation. This is Monterey Formation, a petroleum reservoir rock. Oh, we do this one. This is glauconite. Glauconite's a sort of green pellet-like mineral, if you will. It occurs in relatively deep water in modern settings at places where there's upwelling. So it occurs on siliciclastic shelves as a component of the sedimentary rocks there. In ancient rocks, it co-occurs with carbonates and mostly in shallow water settings. So there's a little bit of an enigma as to how glauconite will actually form in some depositional settings. Why is it not deep water in the Cambrian? Why do you get shallow water glauconite? But anyway, glauconite can actually replace fecal pellets probably, so that's what you see here. So that's the green color is the glauconite, pretty typical color. So we find this in Missouri as well, so it's very common in Missouri. That's a piece of gold from Missouri. This is a brachipod. Brachiopods you can always tell because they're asymmetric, or they're bilaterally symmetrical, but the plane of symmetry actually runs across the valve this way, as opposed to bivalves, which are actually between the valves. So this is a brachiopod right here. Large one, I might add. It's probably a pentamarid. Here's another one right there. And this is a grainstone matrix around it. Now, it's hard to see this, but you can see it better on this rock, which has a lot of crinoids in here. And in fact, it's just chalky full of crinoids. And so the crinoids, when they break, often breaks with the cleavage of the calcite. And so oftentimes when you see a broken surface on a crinoid grainstone, it'll actually show the crystal faces, and so this is very angular because of that. You can actually see the crinoids in here. You can see the brachiopods in this as well. This is a brachiopod crinoid grainstone right here. So all the grains support this. So that leaves us just this one rock. We've already done that one. No, we haven't done that one, have we? This is a flat pebble conglomerate. You can actually see the pebbles on that broken surface here. There's actually a fair amount of glauconite in there. That's what the green is on here. And you can see some of the rusty color where the glauconite is actually weathered a little bit. Oh, there's a shelter pore right there. Check it out. So this was a storm deposit essentially right here. Flat pebble conglomerates occur in the Cambrian and also in the Ordovician. And this is actually from the Davis Formation. It's the Upper Cambrian in southeastern Missouri. And so this has a whole series of pebbles. In some cases, these pebbles are sometimes vertical, and you would call it an edgewise conglomerate in that case. And there may be a component of like water gushing up and reorienting the pebbles in an upright direction. So these things would actually be storm deposits, and then when they would come to rest, they may be like a train wreck, and then the clasts would actually reorient themselves upright, and the water would flush out of them sometimes. But anyway, that's a flat pebble conglomerate, a type of storm deposit, if you will, in relatively shallow water there. Shallow enough anyway for the storm to come along and rip up the carbonates there. And this tends to be interbedded with shales as well. And that's pretty much the story of these rocks.